Hello, everyone. My name is Fernando Miguez. I'm in the Department of Agronomy at Iowa State University, and today I will be presenting a weather and soil databases for APSIM with R, retrieval, manipulation, and visualization. So the outline of the presentation of this is going to be the sources of weather data, a few short R activities, sources of soil data, some R activities, then additional resources. So let's talk about weather data. There are two types of commonly used weather data. One is station data, and the other type of data is gridded or model data. Station data is going to be preferable for when you do point simulations, if that's what you're intending to do with APSIM. There is a need to do quality control on this type of station data. Cross-check it against other nearby stations, or make sure that all the variables are in the correct range. We do need to consider the location, if this is sufficiently close to the weather station sufficiently close to our intended simulation. Often it can be incomplete in terms of missing some of the variables or having gaps in it, so we need to address that. Gridded data is going to be better for regional scale simulations where the intention is not necessarily to reproduce observed data, but to see trends and other spatial structures. We do need to consider the scale of the grid. In this case, the resolution. Different data products have different types of resolutions, and consider whether that's appropriate for your use case. There's also the issue of temporal resolution. For most crop models, such as APSIM, we need the data in a daily time step, but other crop models might need other types of resolution. It is important when using gridded and model data to consider the bias if you're going to apply to point simulations, because some of these interpolations and smoothing functions can create bias, especially when you have things such as topographic relief or lake effects. It is often this gridded model data for our purposes. It can be a better source of solar radiation because of the lack of observations from different sources, but that's something that if you do have good observations of solar radiation, it's preferable to use that. So here I'm just showing you a paper that addresses this issue, and it is titled Impact of Derived Global Weather Data on Simulated Crop Yields. One of the messages from this paper is that on panel A, they're comparing the simulations from using different sources of data, which is the control, which is well-known data from a station compared to NOAA station data supplemented with solar radiation. And what they're basically detecting here is in panels B and C and D is the amount of bias that you can have in your simulations when using some of these gridded products for specific point simulation. So broad recommendations is obtain station data if you can when doing these point simulations. You do need to do quality control. When in particular with solar radiation, notice in the previous slide that I was showing, solar radiation was obtained from a model source, and we often do replace it with another source of solar radiation, such as NASA power, for example. And you might need to supplement data from other sources, whether you have missing data in terms of temperature, precipitation, and so on. When performing regional simulations, one thing I would like to see, sometimes if possible, is to run simulations using more than one source, because this is not very commonly done, but it's important to understand the amount of uncertainty caused by different sources of gridded products. And this might go along with performing an assessment of error, bias, and the variance in your simulations. So now I'm going to transition to talking about weather data sources. I'm going to talk about weather data sources that are specifically useful in the United States and where I'm from, but I'm also going to mention data sources that are applicable in other places. The first one, since I'm here in Iowa, I'm going to mention the Iowa Environmental Mesonet, which it provides data for the whole US and has a number of products that have global coverage. So this is one of the products that is useful for crop simulation. And you can see here that you can select a network in terms of the state. Within the network, you can select a weather station within that state, and then you can select the time frame, the variables, and it has some formats, built-in formats or specialized data formats for APSIM, Century, Daycent, and other models as well. So the data sources that I'm mentioning, this is Iowa Environmental Mesonet. It has station data, it has grid data, it has some of the data has US coverage, but also there's also some data products with global coverage. The NASA Power is a popular source of data, which is gridded and it has global coverage for crop modeling. But often the precipitation and the temperature might not be appropriate for your area. So you need to take that into account. And DayMet is another popular source of data, gridded product for the US. And again, I'm going to show very briefly ways of obtaining that type of data. For global coverage, in terms of station data, each country is going to have its own resources that can be specific. The NOAA maintains a network of stations that have global coverage, so that might or might not be appropriate for unintended use in a different country. For the examples I'm going to show using R, I'm recommend using R 4.0 or higher. The APSIM X R package, version 2.3.1, which is recently published. And I'm only going to show scripts using also the NASA Power package, the required NASA Power package. But there's also data from using the DayMet R as an R package. This package retrieves data from NOAA stations. There's also an interface for chirps, which provides particular precipitation data, but they can be combined with NASA Power. And Fed data is another package that can retrieve certain types of weather data. So for our R activities, first I'm going to show retrieving data. So the weather data with R, when you're in an R session, I'm loading the APSIM X package, and I'm loading here the ggplot2 package for some plotting. The function that performs the retrieval is this get underscore IEM APSIM met, and you can provide the longitude and latitude as this point defined here, and the time range in terms of these dates with the year, month, and date. So there's aims.iem object. Once this run, which it takes a few seconds, has obtained data from the Iowa Environmental Mesonet for this station and this time period. There are a couple of functions that are specific for this type of object, which is going to be of class met. One is a summary function, what I'm going to show briefly, and then there are specific plotting functions for looking at the data. So let's summarize the data very quickly here using the summary. So the summary function, it has a number of options that you can go and search in R, but I'm going to show just one of them. You can select for years a subset from 2018 to 2021, and I will give you some summary information for this years and this object. And with further manipulation, you could prepare a table like this one for, say, a publication. There are a few other options that you might be interested in investigating. For visualizing, the code I was just showing you has a few options for plotting. So this first line of plotting plots the object class met for this particular years. I'm just going to look at a few years, 2012 to 2015. That's going to be easier to visualize. So normally we obtain a graph like this one, and an APSIM interface you obtain a similar graph. But note that this graph makes it a little bit difficult to know what's going on. We only have 4 years, and we have maximum temperature and minimum temperature, but it's not that easy to know, to understand what patterns are going on here. So if we go back to our plotting function, we can select cumulative to be true and climatology to be true as well. And this produces a different graph that allow us to perform an easier interpretation of the data. What do we see here? Well, we have this 4 years. The climatology is the average of the data that we downloaded, which is over 30 years of data. We have the climatology for the minimum temperature and for the maximum temperature. Notice that, for example, a year like 2015 is the purple line. I was pretty close to the black line, so it was pretty close to the average. 2013 and 2014 were a little bit colder in this first part of the year, and then they maintained more or less the average trend, and overall they ended up being colder years on average for the entire year. 2012 really stands out here, both in the minimum temperature and the maximum temperature as being way above the climatology. So 2012 was a very hot year here in the Midwest and in general in the crop growing region, mostly thinking corn and soybeans. But it shows that, it very clearly shows that it was a very hot year. That was sort of hinted in the previous graph, in this graph I've shown you before, but it wasn't all that clear. It wasn't as easy to see the difference between the 4 years. So that's why this graph of cumulative temperatures and plotting the climatology makes it easy to see the trends. And I'm showing you this as a way of recommending a way of observing and interpreting the data for different years that might be a little bit hopefully useful. Similarly, we can look at the data for precipitation. Now the code, the only difference in the code is that here this says met variable or rain. And you'll notice that 2012 was not only a hot year, but also a dry year. So that combination was especially bad for crops. 2013, you started off as being a little bit above average in terms of precipitation, and then it got dry later in the year, and it ended up being a fairly a dry year. 2014 and 2015 here appear above average. Notice here that here in the central Iowa, we get about 900 millimeters on average per year. The cumulative temperature, we might want to look at, I'm producing here a very similar graph, just with 2018 through 2021 instead, more recent years. And notice that the departures from the average from the climatology are not quite as striking. It's usually easier for people to remember last year than previous years, but notice that 2021 we had a fairly warm fall, and this is what you see here, this departure from the previous years. And you can see, for example, that 2019 we had a lot of cold temperatures in the winter, so they were below average. So this is a type of graph that I think, for myself at least, it makes it a little bit easier to compare years, compare and contrast different years, and use them as an interpretation of the data. When we look at the precipitation for this last few years, we see that 2018, for example, was above average in terms of precipitation. That 2019 was more or less closer to the average, to the climatology, and then the 2020 and 2021 were fairly dry years. And So after looking at this data, I was wondering how 2012, which was a very hot and dry year, compares to 2021. So at the end of the year in 2012 and 2021, the amount of precipitation was similar. Remember, 2012 was characterized as being a lot warmer. So that combination of hot and dry was especially bad for agriculture, for crops. But 2012 was under the 2021 was under the 2012 trend, and it only caught up late in the year when it was too late to be beneficial. So I'm showing you these graphs as a way, again, to make it a little bit easier to compare years and contrast them and do some interpretation when we think about how crops perform. I just want to show here that these plotting functions are compatible with ggplot if you do use that package. So you can assign an object, you can use the plot function, which is really plot.met. Here I'm using the summary equals true argument. I'm asking to compute frost days, and I'm going to plot only the frost days variable. And I'm adding through ggplot a smoothing, which is LM, is just a linear model and without the standard error of the regression line. I wanted to show here that we do see a trend in the last 31 years as having fewer frost days. This starts in 1990 all the way to 2021. And we did see this trend, but with a lot of variability from year to year. Some years we have warmer winters and springs and falls, and other years colder ones. So now I'm going to transition to comparing different sources of weather data. This is something that was useful for me when I'm considering using different sources of weather data and comparing this type of data in different ways. I wrote the scripts just to make it easy for me to visualize these comparisons. So here, again, using the APSIM package, you don't need to load it again if you have already loaded it. We extract data from Power, the NASA Power source, and from the Mesonet. This function, compare APSIM underscore here met, I'm extracting the data from NASA Power and from the Mesonet, Iowa Mesonet, and I'm putting labels on those comparisons, and then I'm using this plotting functions for this object, the CMP object for comparing. I'm going to compare first radiation and then radiation in a cumulative fashion. Here you see a very strong bias between the Iowa Mesonet and the Power data. The Mesonet uses modeled radiation. This is not observed radiation in this case, even though all the rest of the data comes from a weather station. And you see that radiation here, we see a substantial number of days, above 30, which we would not expect to see that much. So this strong bias might, how can you know that whether IEM or Power is correct? But I did cross-check NASA Power data for this location against other sources, and the NASA Power data shows less bias. So in this case, the NASA Power data is a preferable source of solar radiation compared to what we are retrieving through the Iowa Mesonet. But this graph makes it easy to make that comparison. The orange line here is the one-to-one line, and the blue line is the fitted line. So you see that they're not close together, and that's the extent of the bias. We can look at the same data in a cumulative fashion and notice how over time, over a number of years, here about 10 years, looking at these two different sources of radiation, the IEM derived solar radiation starts to accumulate and shows a positive bias compared to the Power source. There are many other functions in the package that I'm not going to go into in detail, but that can be useful when working with met data. This is read APSIM met. You can read an object of class, MET object, typically using APSIM, into R. You can write a MET object class MET into a MET file, so that can be imported into APSIM. You can check for reasonable variables and ranges for the APSIM MET format. You can do imputation if you have missing data. NA_pad is a function that will fill in gaps with NAs or not available, which can be used for further imputation. And here I'm mentioning also this daymet function, for example, that requires the daymet_r package that can obtain data through in that way. And there are a few other functions that obtain data from other sources. There's this file, this document is right here in this location. So you can go and look at it directly. So that's it for weather data. I'm going to transition now to sources of soil data. So let's talk about soils. Soils are obviously different from weather, but in terms of the data, they're different because we have fewer sources of soils data, and just the nature of soils. You can see here, the soil profile. They're more spatially variable. They're going to be less specific for an individual point. You do need to consider the depth component. The characteristics that vary within the depth of the soil are very important for crops. Soil sampling is costly, so of course, all this data that we can obtain through different weather data sets are an initial guess, but whenever it's possible to conduct some soil sampling, that's preferable for obtaining good quality information for our simulations. Here I'm just showing the nature of soils, which this is not a class about soil taxonomy or soil pedology, but just the nature of soils and how they vary, and we have the different horizons and so on. But I just want to transition now to different soil databases that we use. The first one I'm going to talk about is the Sorgo database, which is specific to the US. There's a gridded version of Sorgo that can prove useful. And then I'm going to talk about soil grids from the ISRIC. And there are other soil databases, which I'm not going to mention here, but that can be useful in certain applications. So talking about the Sorgo data, the nature of this data, if you, this is a place near us, but here Ames, you can see the different polygons describing variation in different soil types and different identifiers. In the Sorgo database, we have map unit keys with a given polygon with a given map unit key again that identifies this area. Within that map unit key, we can have different components with some major components and some inclusions here. These are going to be different idealized soils, really the average of a number of samples. But what I want you to notice here is that for a given point, we don't have certainty of what kind of soil we have there. We just know that there are probably a few different types of soils at that particular location. Within those soils, those soil profiles, we have different horizons that describe typical properties, soil properties, that we can then extract and use in our analysis. If you're not familiar with the Web Soil Survey, it is, if you do need data from the US, it is worth using it and trying it out. This is the website for this web page, and you can start. The Web Soil Survey will take you through a portal like this one, where you can go here and define an area of interest. And for this area of interest, it will give you the ability to explore. that data. For example, here I'm looking at organic matter, and with it, that area that I selected, I get different this map unit symbols and different soils here. The names of the soils are Okoboji, Nicolette, for example, Clarion, Canisteo, and so on. The numbers you see here are ratings of organic matter, and here we see the acres in terms of the area of interest and the percent that they occupy. So here we see that this Canisteo soil occupies about 61%. You can find more information about this under these two links, so they might prove useful if you're not familiar with some of this terminology. When you select data in Sorgo, you can download the data as a zip file for a given area of interest. And once you download the zip file to your computer, you're going to see something like this. So it can be, if you're not familiar with the Sorgo database, it can be somewhat intimidating. So we have a lot of files that have the spatial files. So in this case, I obtained 29 spatial files. There's this object here, MDB, which is Microsoft Access Database. Can be useful. We also have a lot of data in a tabular format, and we have 71 of these text files. Navigating through all this information can be a little bit daunting if you don't have previous familiarity with Sorgo. So for this purpose, you see this map right here. I was done in R, and I'm going to show easy ways to access the Sorgo database in R for the manipulation. So for this particular location, you see some of the same data that I was looking at previously through the Sorgo portal, but here they're ordered from the one that occupies the most area to the one that occupies the least area. So how do we retrieve that data and visualize it and perhaps manipulate it in R before we use it in APSIM? So for this, you're going to need the APSIMX package again, and I'm using the SolDB package behind the scenes, but it doesn't need to be loaded in a session, it just needs to be installed. And you might need other packages in case something fails, some dependencies and so on. So here I'm using this function get Sorgo tables, which with just point, again, longitude and latitude description, it will download just the tables, those tables and the relevant shape files that we use for crop modeling at this point. And you see here that I'm using the names function on this object just to see what kind of things we have in there, what kind of object it is using the class function, and then what do we have in terms of the spatial component. So this is what happens when you run that in R. This function takes a few seconds to run, which retrieves the data. It performs a query to the Sorgo database, and it just brings that data into R. It is going to have 4 objects within this structure: a map unit, component, C horizon, and the map unit shapefile that was just described. It is a list, which is a common structure in R, which can, within this list, you can have objects of different types. The map unit.shp is equivalent to the shapefile that you would obtain through Sorgo. And it's an object which is the geometry. It's a spatial object in R. It's a simple features collection. It is a point, and it has those coordinates, and it tells you what the map unit key is for that given point. So the figure I've shown you before, you can retrieve an area. I did this just for simplicity. You can use a shift argument with this number here, 300, which represents the number of meters that you can draw a square, starting with this as the southwest corner. And you can draw a square of 300 meters by 300 meters. here this line of code just converts this map unit as a factor, which is needed for further plotting. And I'm just using the plot function here, generic, for looking at the map unit key, and this key position 1 puts the key for the graph at the bottom. You see that you might be interested in defining a different area of interest, and that is possible as an additional argument to this function. This is what the map looks like, where we have, for this, your area of interest, we have different soils, different map units, which are going to, in themselves, and again, within each polygon, you're going to have several soil types, different soils. But we don't know exactly what those soils are. So that gives you, what I showed previously, gives you access to data directly as present in the Surgo database. But this function, get_Surgo_soil_profile, creates an object which is specifically tailored for APSIM needs. And here, notice that I asked for a single point. Within that single point, we're going to have just one map unit, but I can ask if there are they can be one or more soils within that map unit. And here I'm asking for just 2 soils. And there could be more potentially within that polygon. Here, notice that I'm using these double square brackets that are used in R for accessing objects within a list. And I'm looking at what the soil type is. The map unit key is the same, but the name of the soil here is Clarion, and this is Storden. So these are different soils within that polygon. So we can visualize that data, and we visualized some of it already in a spatial format, but now I want to visualize it in terms of its depth. So by default, that function get soil profile will create a soil profile with a given number of layers, and it just does an interpolation. You can sort of create more layers or fewer layers, and you can define what do you want to be the thickness for each layer. So here I'm just accessing that first soil, and I'm plotting the property carbon, as you will see it in APSIM as well. So I'm now going to compare. You remember that I downloaded within this SPS object that I downloaded before in that line of code. Again, it takes a few seconds. There were 2 different soils, Clarion and Storden. And if you perform different simulations with different soils, you're going to be interested in knowing why the APSIM output might be different, which variable might be causing the differences in your APSIM simulations. So this allows you to make a comparison between properties, different soil variables. So here I'm just going to compare Clarion and Storden, and I'm going to look at the soil variable carbon. So we can see here that for that particular area where we extracted soil from, Clarion has a higher soil organic carbon at the top layers. And then here it's about the same. It declines and down as this depth, it gets lower, and they get more similar as they go down. So this is just I'm showing you basically some art code that makes it easy to produce these graphs, which might aid in the interpretation of why perhaps otherwise identical APSIM simulations can produce different outputs depending on the soil. And so this allows us to do that. As I mentioned, that the Surgo database is applicable, if I'm going to move this up a little bit, applicable for the US only, but you might have interest in obtaining data from other places. The Soil Grids website from is a very nice website. I can also recommend it if you want to obtain data from different parts of the world. But again, the Soil Grids database is not specifically tailored for APSIM. So how can we obtain data that we can easily impute into APSIM? So I'm here showing you that with this line of code, get asterisk soil profile, we can obtain for that same point that I was using before. It can retrieve a soil profile that is suitable for use in APSIM, and this plotting function that can produce a graph similar to what you see in the user interface for the property water. We see the saturation, the drainage upper limit, lower limit, and the air dry. So before I go into additional resources, you might be wondering, the capabilities in APSIM. And APSIM allows you to download some of this data with a right click, APSIM Next Gen, for some weather data and some soil data. But often it is important that you don't just take that data at face value and perform some quality control, some analysis, and I find R to be a useful tool for that purpose. So my recommendation is not just to simply download data and trust that the data is going to be correct. It is important, if you are interested in accurate simulations, to perform a visualization, analysis, manipulation, etc. of both weather data and soil data. So now I'm going to finalize my presentation with a few additional resources. If you're watching this presentation, you're probably aware of the APSIM initiative training videos. There are a few related ones. One, for example, about calculating thermal time in APSIM, which the APSIMX package has some functionality as well. There's a video in a related channel by Matthew Harrison about understanding APSIM next generation weather, where you can see more of the interactive use with APSIM. There's another video about soil weather experiment and calibration that you might find useful as well. Finally, there's a recent publication which can also be useful for some of the viewers of this video, which is a protocol for building soil descriptions for APSIM simulations, which was published late last year. And there's also additional very useful information in the APSIM website, both the .info and the next generation one. And another source of data or tool that you might be interested in is a Python package called Bestia Pop, which can also download data, weather data. So with that, I'm going to finish my presentation. Hopefully you found it useful. I admit this had a bit of a bias to the tools we use and which are applicable in the United States, but I try to cover tools that are useful in other places. So with that, thank you for watching, and I hope you have a good day.